All right, guys, so section 5.5. Section 5.5, a couple things we want to clear up here. Number one, is we look at the title. Again, this is, again, in accordance to our textbook. Section 5.5, what our textbook titled this, multiple angle and product to sum formulas. Just so we're clear, we're not going to be doing much of anything with the product to sum formulas. Okay? And it's, I hope you believe me when I tell you, it's not because, oh man, these things are so difficult, they're so hard to work with that we're going to avoid them if we can. It's not it at all. It's just that literally any problem that we would use the product to sum formula, we could already do with the sum or difference, or we could do with what we're going to talk about with these multiple angles. These multiple angle formulas, we're going to have two different types that we studied. We're going to have the double angle formula as well as the half angle formulas. So with your knowledge of what we were trying to accomplish yesterday or / today with section 5.4, the sum and difference formulas, the theory or the thought process is the same. What do we do if we have angles that we want to find exact values of, but they're not one of the 16 spots on the unit circle? Can we use these spots on the unit circle to pinpoint or to target a specific angle? Okay, like for instance, we've already talked about how we could get to like the cosine of 15 degrees. But another way that we could start to think about this, once we get through the half angle formulas and how they work, do we understand or recognize that 15 degrees is merely half of 30 degrees? Well, we're going to have a formula that gets us there. Okay? We're also going to have formulas that get us to the double angle formulas. But we're actually going to notice relatively quickly that we're not really focusing on the number side of things. Because again, how are we going to pull that off? Oh, I wanted to get to 90 degrees. Why would we turn that into 45 doubles? We could just get to 90 degrees. If that makes sense. So what the double angle formulas are actually going to, the role that they're going to play is much more like what we had with identities. Again, the good news here is that no, you are not going to have to memorize the double angle or the half angle formulas that we're going to introduce in section 5.5. It's just like the sum and difference formulas. Can we apply them? Again, are we able to perform the application? It's not the memorization piece. Okay, so I'm expecting or anticipating that we're going to do pretty well with this stuff too. It's really just a matter of seeing when and how, I suppose. All right. So again, we are going to split this up as we said. Today, the remainder of time that we have, we're going to talk about the double angle formulas. Tomorrow, we'll get into the half angle formulas. So again, our goal today, students will be able to use double angle formulas to rewrite and evaluate trig functions. There's going to be a lot of things that we can do with them. So again, kind of a cop-out way of saying that, to rewrite and evaluate trig functions. That actually covers a lot of things. So here they are. These are the double angle formulas. They are in your notes. They are on your buddy sheet. I've written them up here on the board. Again, we just want you to have multiple visuals all over the place. Just upon first glance, hopefully one of the first things that comes to mind is that when we look up there, we see, all right, sine, double angle, pretty straightforward. Tangent, double angle, pretty straightforward. Cosine, we have options. Okay, so are we going to have to use all three of those for cosine? Absolutely not. It's just that we have three ways that we could get there. Three different plans that we could implement, I suppose. Again, with the cosine of 2u or cosine 2 theta, cosine 2x, again, cosine 2, put a star there. We just need to hold the spot for an angle, as we've talked about before. But the cosine of 2u is going to be equal to 2 times cosine of, or 2 times the sine of u times cosine of u. So like I said, we're going to be using this as an identity fairly often. Like for instance, the first example that we're going to be getting ourselves into, it's somewhat played like this, where if we have the sine of x plus the sine of 2x. Well, we can't combine these because my angles don't match. But could I use a double angle formula to get this back in terms of just x instead of 2x? And again, we'll practice this here a little bit. But we have the ability to use these double angle formulas really. And again, I'm trying to think if it's going to be better to say this or talk about this now or not, wait until we get to a couple of examples. What you're going to notice is, we'll just talk about it here and now, is that in many cases, this is going to be a tactic. Really, it's an extension of section 5.3. We're going to use these to be able to solve equations. Okay, just like we were doing in section 5.3. But what if we run into a little bit of a roadblock and we have one of our angles that's not cooperating? Okay, like for instance, if we had, I don't know the best way that we could say this, if we had something like the sine of, again, not that this would ever happen, 30 degrees plus the sine of 60 degrees. Well, we could turn one of these into, using the double angle formula, we could turn that 60 degrees, because right now we can't combine these yet. Now, I know that you're probably saying this is a stupid example. I agree. Why wouldn't we just evaluate them and figure it from there? I completely agree with you, but I'm just trying to show you something that, that might help out. Could we think of this instead as being sine of 2 times 30 degrees? And we start to see, oh, well, that's just the double of this angle. And then we could start to plug in, and then we could rewrite this whole thing to be in terms of 30 degrees instead of 60 degrees. You guys kind of see where we're going with this? And that's going to change the game for us a little bit. And once we implement some of these things, like I said, as more of an identity, that's when we're going to have the ability to solve the equations. So I don't know if this is good news or bad news, but the bulk of the work is going to feel like what we were doing in section 5.3. You're going to be solving equations. It's just that we might have an interesting step in there as far as, well, I can't solve it the way it sits, but if I do this, now I can solve. That's going to be the type of thing that we'll experience. All right? So another thing that I'd like to talk about here, again, sine and tangent is relatively straightforward. Again, cosine, when do we use the first, the second, when do we use the third? And really, I do understand it's kind of a cop-out answer, but it's totally dependent upon the rest of the problem. What else are you given? If you have everything's in terms of sine, this bottom one's probably going to be our best option. Wouldn't you agree? Again, we're going to want to utilize this and plug that in its place. If everything else is in terms of sine. If everything is in terms of cosine, then yeah, we're probably going to want to use this middle. Again, fair thought would be, you know, are we ever going to use the top? And the time that we would use the top is if this is going to lead to a cancellation. Like what if we had sine squared plus cosine 2u or something like that, and now all of a sudden we plug this in and sine squareds are going to subtract up. That's typically the time and place that we would use this top option. All right? But really, it would be irresponsible to say, oh, we always do it this way or that way or this other way. It really is just dependent upon the problem. And in many times or many cases, you're going to have complete choice. It's totally your call as far as which one you want to use. Okay? All will lead to the same answer. All right, so first up, this first example, we've got 2 times the cosine of x plus 2 sine 2x equals 0. Okay, so this is what I was trying to get at before. My angles don't match. That's a problem. I cannot combine these. Even if I had common trig functions, which I don't. I have cosine on the left, sine on the right. But right now, I cannot combine these whatsoever. Luckily, sine 2x, this is where we look and say, oh, that's the opportunity for a double angle. So can I rewrite as 2 cosine x plus 2 times, and in place of sine 2x, can I rewrite that as 2 times sine x cosine x? Isn't that what the double angle says to do? And that's equal to 0. All right, so I'm pausing here. Does everybody understand what we just did? Now, if you're thinking, oh, it must be solved. No, we got a lot of work to do from here. But at this point, this is now a 5.3 problem. Do we understand that? That we've done the 5.5 double angle work. Now it's just, hey, let's go ahead and solve. So hopefully our key recognition is that on the right side, we're equal to 0. What does that mean that we want to try to do on the left side? What's that? Again, we have options for sure. But if I have a 0 on the right side, if I have a multiplication problem on the left side, we're going to be in good shape. Okay, that's a trick that we've used multiple times. Right now, we don't have a multiplication problem. We could work on that. So what am I going to do here? Looks like we're going to multiply. So 4 sine x cosine x. Now again, we don't have a multiplication problem yet. But think about how we just create multiplication problems. Could I factor something out? Because if I can factor something out, then it turns very much into this thing times this thing. So what could I factor out of this problem, please? 2 cosine x factors out. What's that going to leave me with here? 1. What's that going to leave me with here? 2 sine x. Everybody see what we just did? We don't want to leave anybody behind here. Does everybody see that we just factored out a 2 cosine and that left us with 1 plus 2 sine x? We need some kind of like a visual, like a head nod or a thumbs up or something. All right, are we seeing that? I keep hitting the wrong button there. All right, so we're good to proceed? So we plugged in, we recognized that sine 2x, that was just a double angle. So in place of sine 2x, I put 2 sine x cosine x. That's our double angle formula, right? So then from there, when I multiplied 2 times 2, that gave me 4 sine x cosine x. We didn't touch the 2 cosine x yet. So now that means on my entire left side, we have 2 cosine x plus 4 sine x cosine x. We're looking to factor something out. What could I divide out? What's the common thing that I could divide out of both terms? We said that we could factor out or divide out 2 cosine x. So if I took 2 cosine x divided by 2 cosine x, that's how we got 1. If I took 4 sine x cosine x divided by 2 cosine x, that left us with plus 2 sine x. So again, if on a totally unrelated note, what if we had something like 2y plus 4xy and it equals 0? And we want to factor on the left side. What would I factor out? 2y. What's that going to leave me with? 2y divided by 2y is just 1. 4xy divided by 2y is going to be 2x. Like that. Does that make sense how we got there? Yeah. Okay. So even though this one looks more complicated, all that I did was I put in, what did I put, I guess? Oh, y in terms of cosine x and an x in place for sine x. Okay? Coefficient stayed the same. So it's the same process. It's just that we're very used to working with it algebraically. We're not nearly as used to working with it in terms of trig. Okay? But once we're here, I have this thing times this thing and it equals 0. So we're going to set each factor equals 0. So we're going to go to say, go ahead and say, I should say, 2 cosine x equals 0. And here in a minute, we're going to say that 1 plus 2 sine x is also equal to 0. So we're going to solve these separately. I'm trying to isolate the trig function, so I don't want 2 cosine x. I just want the cosine x. I'm going to divide both sides by 2, and we have it now. Cosine x equals 0 divided by 2 is 0. Now the question becomes, where in the unit circle is cosine equivalent to 0? What are we going to say? We're not going to say anything. Okay, well, I'll say it then. Pi over 2 and 3 pi over 2. All right, now, regrettably, I did a very poor job of writing directions. In fact, I just kind of didn't. But it definitely doesn't say we're only solving over the interval 0 to 2 pi. So all indications would be that we want the complete solution. So I have to add the period times n, plus 2 pi n in both cases. So here's our first solution. Here's our second solution. There's no overlap, so we have to keep both of them around. Okay? So that's what we did on the left side. Now we're going to do the exact same thing on the right side. I need to isolate the trig function, so I'm going to subtract the 1 over. We have now 2 sine x equals negative 1. We're going to divide both sides by 2. Sine x is equal to negative 1/2. As we used to say this back in section 5.3, we should be excited about this because not only do we isolate the trig function, but we recognize the value as being from the unit circle. So now where on the unit circle is sine equivalent to negative 1/2? What are you going to tell me, please? 7 pi over 6 and 11 pi over 6. Remember, we need the complete solution, so plus 2 pi n. In both cases. There's no overlap, so both of these are part of our solution. So all 4 of those are our solutions. All right. How do we feel about this, guys? Okay, I'm going to stop the video.